Okay, so this is my first video on rotational matters in physics. Okay, so what we have here is we have a disk. Well, technically it's a flywheel, and you can see, and it's the round circle, and then there is like a bar or a rod that's going through it, right? Right here. So this rod's going through it, and yeah. So this wheel is spinning, right? And this wheel has a certain amount of mass, okay. And so what I want to do is well, first of all, this wheel has what's called a moment of inertia, or I, and it happens to be 12. So actually, let me turn this. Hold on a second. Let me turn this thing off. Okay. Excellent. So the moment of inertia is 12. What does that mean? So it's like in linear motion where you have mass, and mass resists changes in velocity. So if you're moving, so if you have a certain mass and it's moving, if you want to change its direction or change its speed, i.e. change its velocity. Changing velocity means what? Acceleration. So if you want to change its acceleration, or if you want to accelerate the object, meaning you want to change its velocity, either position or speed, it's going to be harder and harder the more mass it has, because the more mass it has, the more it resists those changes. Well, it's the same thing for things that are moving in a circle, but it's not only mass that resists the changes in velocity as you move rotationally, but it's also the mass and how the mass is distributed along the rotational axis. Okay, so this thing here, right? So there could be like more mass here or less mass here. Like the mass in this area here could change as you're moving from the center out. Right, as you move out, there could be more or less mass. Okay, and so what you need to do, of course, is in order to find the I, which is the moment of inertia, is you have to find not only its mass but how the mass is distributed along from the center out. And you can either, if it's in discrete chunks, you can just multiply the mass times its mass times radius. At some point, like for example here, and then you can multiply the mass times the radius here, and then you can multiply the mass times the radius here, and then you can add those up, and you can get the total moment of inertia. But if something is continuous, obviously, you can't do discrete additions, so you'd have to do calculus, and you'd have to integrate over that area, right? So if it's discrete, you can use sigma notations, right? Because you can just sum up. Sorry, it's not that. You can just sum up the mass and the radius. Well, it's radius squared. Because what happens is as the radius is increasing, the moment of inertia increases with the square of it. So it's not like a linear representation, like, oh, you go a little bit more distance away from the center, it's just a little bit more inertia. No, so it gets really worse the more distance you put, because it's the squared of the radius. So I is that. But if it's not discrete, if it's just like some continuous blob, obviously then you'd want to integrate the mass and the radius squared. Okay. So anyway, so that's what the moment of inertia is. The moment of inertia is just how much that wheel that's spinning, how much it's going to resist changes in velocity, i.e. acceleration. Okay? So we have this thing that's spinning, and it's spinning at, it has an inertia of 12. It also has an initial kinetic energy of 30 joules. And what I want to do is this thing is going to slow down. This wheel is going to slow down, and so I'm going to do KE0 for initial, and then I'll do KE final 1 for final. Is this going to slow down to 15? 15. I don't know what that's a J. I was reading my own handwriting. 15 joules. So it's starting out of 30 joules of energy, but it's going to slow down, and then when it slows down, it'll have 15 joules of energy. Okay, and so kinetic energy, you may remember, is just 1/2 mv squared. But that's for linear motion, and this is rotational motion, so you have rotational kinetic energy. You could still say kinetic energy, but I'll just, for this purposes, I'll just say, oh my god, that's hard to read. Let's say rotational, R-K-E. And it's very similar. It's 1/2, and then mass is, but in the rotational sense, you have mass, but it's mass distributed along a radius. So you can't just say mass. You have to use mass times radius, or the moment of inertia, I, capital I. And then V, in linear sense, V is just velocity, but in the rotational sense, it's called angular velocity, which is called omega. So the Greek letter omega. And then we're going to do squared. So you can see in linear motion, it's 1/2 mv squared. In rotational motion, it's 1/2 I omega squared. So you can see it's very similar, or it has very similar analogs. Instead of linear velocity, it's rotational velocity. Instead of linear mass, so to speak, it has rotational mass, so to speak. Okay, so we have this spinning thing. It has an inertia of 12. It has initial kinetic energy of 30, and then a final kinetic energy of 15 joules. Okay, and I want to so this thing is going to slow down. Well, how fast is it slowing down? Well, the acceleration is 0.5 revolutions per second squared. Okay, so it's acceleration. So the denominator is going to be in seconds squared, and the numerator here, in linear motion, the numerator would be like meters per second squared, right? Meters, kilometers, whatever. We typically meters, but because this is angular movement, it's going to be in some sort of like angular unit, like revolutions, degrees, or most commonly radians. All right. So we have a wheel. It's moving, right? And it has 30 joules of energy. But we're going to slow it down using this acceleration, or deceleration, if you will. We're going to slow it down, and then as it's slowing, the energy is going to go from 30 to 15. Now the question is how long is that going to take? Time in seconds. That's what I'm looking for. How much time is it going to take as I'm slowing down to go from 30 joules of kinetic energy to 15 joules? Okay, so let's do this. So the first thing we want to do is, we have this acceleration in revolutions per second, but I want to change that to radians per second squared. Okay, so if I have 0.5 revolutions per second squared, and remember I want to convert this just to radians per second squared, times. So I'm going to say 1 revolution is equal to how many radians? Well, remember in a circle it's 2 pi radians. So pi is like, so if you have a circle and you start here, this from here is called pi. That's pi radians. So it's about 180. Well, it is 180 degrees. So if that's pi, then to make the full circle, it of course is 2 pi. 2 pi. So back over here. So there's 2 pi radians in 1 revolution. So I can get rid of that. And then basically now you have 0.5 times 2. That cancels out, right? So then basically you're just left with pi radians per second squared. And that's the acceleration. Okay? So let's highlight that. So now we have the acceleration. Well, technically it's negative because it's slowing down, right? So if it was speeding up, it would be positive pi. And of course, pi, remember, is 3.14. So that's what this thing looks like. All right, so let's sort of graph this out. What I like to do, typically is graph these things. So let's look at this. So I'm going to start off, and I'm going to do this as in omega, which is going to be in radians per second. Remember, omega is speed in degrees or radians per second, okay? And then we'll have time here on the x-axis. So what's going to happen is this thing is obviously spinning, right? So it's going to have some sort of speed, some sort of angular speed, omega. And it's going to slow down. And how is it slowing down? Well, it's because acceleration is slowing it down. And is acceleration constant? Yes, it's constant. So we can just make this a line. We can just make that a line. And what's the slope of this line? Well, it's negative pi. So I can say that omega, as a function of time, is negative pi t. Okay? If time is 0 seconds, 0 times pi, of course, is 0. If it's 1 second, 1 times pi, of course, is just 3.14. Negative, so I'll have negative 3.14. If it's 2 seconds, 2 times pi, roughly 6 seconds, negative 6, etc., etc. So this is going to tell you t. If you pass in a t, I'll tell you what the speed is. Okay? You give me a t, I'll tell you what the speed is. But there's a y-intercept here. That means how fast is this thing going initially? So if I say right now, how fast is it going? Well, I don't know. Okay, but what we do know is it currently has 30 joules of energy, right? So it has 30 joules, and so that's energy. And so remember, energy is equal to 1/2 mv squared. Well, that's the linear case, but this is I omega squared, okay? And remember, I is 12. This is 12. This is half. This is omega. Half of 12, of course, is 6. And this is omega squared. And this is still 30. And then I can do 6. Get rid of this. And 30 divided by 6 is 5. 5 is equal to omega squared. And I'll just take the square root of that. And so then omega is equal to the square root of 5. Radians per second. So I use the energy of this disc, of this flywheel. I use its energy to figure out like how fast is it going. Yeah, and so it's square root of 5. So we can say square root, just to I mean, you could write out the actual decimal value, but just to keep everything exact, let's just write square root of 5, which is roughly, like 2 point something, right? 2.2. So over here, I can do square root of 5. So my formula for this thing, for this spinning thing, is if I want to know how fast it's going at any particular time, I can just pass in the time, and I multiply times pi, and I add the square root of 5, and that will tell me how fast it's going. Whatever, at 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, a million seconds, whatever. Okay, so that's cool. Now, the other thing I want to know is so that's cool, but I want to know. So when this thing slows, it's gonna have 15 joules of energy, right? Right now it has 30 joules, but it's gonna have 15. So you could say 15. What if you had 15 joules and you did 1/2 I omega squared? What would that look like? So remember, I is still, that's like your mass and your radius. Is that going to change? No, it's still the same. So it's still 12 divided by 2 is, of course, is 6 omega squared. 15 equals 6. Get rid of this guy. And then so we have this. Basically we have omega is equal to the square root of 15 divided by 6. So this is its speed, which is roughly, if you're like, well, what is that? It's about 1.5, if you want a number. So this thing is going at square root of 5, or 2.2, and it's going to slow down to 1.5. And once it's slowed down to 1.5, or we'll just write it right here, we'll just do, just to keep everything exact, we'll do square root of 15 divided by 6, okay? Which, like I said, is about 1.5. Okay, so let's put, and then let's do this. Okay? So now we have two lines, right? So let's put this back here. We can say, whatever, you can call this one like F, like final. It doesn't really matter. Times t is equal to square root of 15 divided by 6. Okay, so I have two functions. I'll call it w of t, and I call this other thing f of t. Okay. Okay, like there. So what I can do is I can set these two equations to them equal to each other. So I can set w of t equal to f of t. And when I do, what I'm trying to do is I'm trying to figure out where do they intersect. Where do these two functions intersect? So I can say, where does omega t, where does that equal f of t? Okay, where do they equal? And so omega t is what? Well, it's negative pi t plus square root of 5, and then f of t is just, it's not really a function of t because t's not in it, but it's the square root of 15 divided by 6. Okay, so obviously you just have this right here, and I just need to solve for t, right? And so yeah, so if you just solve for t, you end up with 0.2. So from here, t equals 0.2. I believe it's 0.208 seconds. So right here is 0.208 seconds. Let's just highlight that, make it yellow because why not? Okay, so and that's basically it. So in about 0.2 of a second after this thing starts deaccelerating, this wheel's gonna go from 30 joules of energy to 15 joules of energy. Okay, and of course, obviously, if you keep letting it go, keep letting it slow down, obviously it's going to stop. And you could figure out, when is it going to stop? Well, it's just that when you just set omega t equal to 0. 0 meaning zero velocity. So when does it hit zero velocity? So you could find out when is it actually going to stop. But yeah, so this problem here, like I said, we looked at this rotating thing. I talked about I, which is mass and the radius, which is mass spread out over the radius. We talked about linear kinetic energy versus rotational kinetic energy. We converted revolutions per second squared into radians per second. And yeah, then we use these graphs, which I like to do, like the position, velocity, acceleration, whether it's linear or rotational. I like to use these graphs because it kind of helps me visualize what's happening. Yeah, and then we used basically energy and rotation to try to figure out how long is it going to take to slow this thing down to where we go. We basically half the energy. All right. Okay, that's it.